How was your weekend?
I went camping.
Oh, where'd you go?
Down Shelf Road.
Where?
Near Colorado Springs.
Oh.
It was really nice. We went rock climbing.
Did you go 2 nights?
Yeah, with OEP. We only went one night because people actually come back on Sunday.
Oh, okay.
But it was nice.
That's cool.
Yeah.
Oh, that's great. Do you have your own camping gear?
I don't. I had to rent some stuff.
Yeah, they got a good setup though, right?
They do.
They got a good rig.
Yeah.
And was Kitra there?
Yes. I love Kitra.
Oh, yeah. I mean, it's hard not to, right?
Yeah.
What a dynamic human being. Oh, it's on tape. I'll play this for her. Later.
Did you see Nick?
Yeah, I love Nick.
Who else? Who?
Nick. He's Alex's sweetmate. Right?
Oh.
Yeah.
Oh, right.
Super
the guy I
rock
called
star.
you for a couple
Yeah,
times.
yeah,
Yeah.
that's right.
Okay. All right. So, my friends, I think we're gonna have our exam 2, around the week of November 7th.
Okay.
So around
About a
what's that?
About a month.
It's not quite a month.
Oh.
I think it's like 3 weeks.
Yeah, 3 weeks.
Yeah. So in about 3 weeks,
Okay.
I think we'll be having that exam. I don't know the exact date yet, but you were actually asking me last time, so I wanted to get you that information. We're going to talk a little bit today about Big O notation. And there's actually, like, some persons, Trayson's already done with the homework, right?
Yeah.
Yeah, so that's good. I did open a prep, I did create a new prep for Wednesday, so you'll have something to do. So I knew you'd be worried, you wouldn't want to sit here and not have something to do. I'm just messing with you, Tracy. But I did think about you with that. And so I just want to talk a little bit about this. You will be applying this stuff in your CS classes. So we're not going to apply it, we're just going to talk about, like, what does it mean, and then look at a few algorithms that we've already talked about, and one actually called the TIM sort. Have you ever heard of TIM sort? I hadn't either, but there's a TIM sort. So I was like, okay, what's all TIM sort about? And so we'll talk about the Big O notation in relation to those things. Let's get rolling. So first off, let's say I had a piece of code, and actually let me put a piece of code up here. So a simple one. So I've got this procedure, I'm just gonna say proc, it just adds some numbers together. So add array, so I pass in an array, I'm not showing the domain hell, okay, whatever. The domain is reals, there we go, because we've been doing that. Sets this variable sum to 0, and then for I in the array, so it's grabbing the elements out of the array one at a time, and it is adding them up. And then it returns that sum. So this is one algorithm right here. So each time I go through, as the size of the array increases by 1, how does the number of operations increase in here? So if I've got an array with 10 things in it versus an array with 11 things in it, what is the difference? What is happening here? How much longer does it run? One extra loop, right? So for each increase in the number of things I'm passing in, I just get an increase in the repetition of this loop here. So it just runs an extra cycle for each extra element in here. If I were to run this on a computer, and let's let n, so n here is going to be our array size. And so, maybe I'm just kind of curious about this, and I have another bigger program that runs this thing over and over again, and each time it passes in a different n. So like one time it passes in just an array of size 10 and adds up the 10 values in there. This is going to keep track of the processing time. So maybe, I don't know how many milliseconds or microseconds it takes, but let's just say it looks like that. And then I pass in 20, 30, 40, 50, and I maybe go up to 100 or something like that, but each time I'm just plotting the processing time associated with that array size. And I noticed that if I do this enough, and maybe I've added some extra data points in here, it varies. So there's no clear pattern among the dots, but there is kind of an overriding feel to them. And I could notice that maybe I could even draw a line straight through there. And so this kind of syncs up with the idea that for an increase of 1 in our array size, I have just a finite increase in the processing time, or a proportional increase in the processing time. In fact, the slope of this line gives me a sense of how much the processing time will increase given a 1 unit increase in the input time. But more importantly, it kind of gives me a sense of what to expect when this data set gets really, really big. So if I pass in 1,000 things, I could easily kind of predict how long this would take just based on this. So out here at 1,000, I just keep this line going and follow it and make an estimate using that line of how long this would take given 1,000 data points, or maybe 10,000 or 100,000, or even something even crazier than that. So this is one scenario. And that would probably be a pretty realistic output for this piece of code. Now, what else could happen here? Well, it depends on the machine I run this on. So if I run this on an old 386, do people know what 386s are? Like just ancient computers. So I run this on a really old computer, like from 1985 or something like that. Maybe it looks like this, and I run it on a current machine, and I see a completely different pattern. Actually, that would be an older machine. Here's a newer machine. Sorry. It runs faster on a newer machine, but the response to runtime versus input size is kind of the same rhythm. I've got a line here. I've got a linear response in the processing time. If I had a really old computer, that the dude with the cardboard or the wooden paperclip computer, maybe I'd have a response time like this. So this is a really slow computer because to do a few things it takes a while to do. This one's a really fast computer because to do a lot of things is even faster than this one here. So this is a faster machine. This is a slower machine, but they still respond the same way. What I want to describe to someone who sees this algorithm is, what kind of response do you expect, independent of the machine you run this on? And that's part of what we're going at today. Let's take a look at another example. We have got a new procedure. So this procedure is add up the first 10 digits. So I'm going to change this routine. So I've got a new proc. Okay, I'm not going to use that pen. I keep putting the rotten ones back in the batch, so proc, add 10. And so again, I pass in an array, and they're reals. And this one's going to set the sum to 0 again, but now for I equals 1 to 10, I'm going to go up to 10, sum equals sum plus array element I. So this just accesses the ith element of the array and adds it to the sum, and then I'm going to return that. What kind of response do I expect from this code? So let's make a little chart. So we've got size of data set, the original data set, and then here I've got processing speed. So here's n equals array size. What do you think it would look like? Yeah, there's 10, 20, 30. What kind of pattern do you think we'll see? What you thinking, Yvonne?
I don't know. I was thinking, wouldn't it be constant time because you're only running at 10 times?
Yeah, exactly. So check this out. This piece of, yeah, that's exactly right. This piece of code doesn't actually even know how big the original array is. It's just going to do its same thing independent of the actual data. So this one's going to look something like this. You know, and there's a little bit of variation. It's never a perfect line, but what I do see is this constant response. What would happen with a faster machine? What would it look like relative to that data set? Yeah.
It would just move the horizontal line.
Absolutely, it's just going to run faster, right? So this is that original slower machine, and then here a faster machine is going to do this, but it's still going to have a linear response. So here's a slower, and here's a faster machine. Let's look at one more case. I'm going to have to erase this left side, so I hope that's okay. So this algorithm is a little bit more complicated, but nothing, you know, no bubble sorts or anything like that. Just a little more straightforward. So I've got this procedure, and let's see, what did I call it in my little notes here? Add more. Now that's very descriptive. Add more. And I'm going to pass in an array of reals. And then I'm going to kick right into a for loop. So I've got for I equals 1 to n. I'm going to set the sum. So now this is indented. I'm going to set the sum variable equal to 0. And then I'm going to go into a new for loop. For j equals 1 to I. Sum equals sum plus j. How about we just say array j? Yeah, array j. I'm going to grab the jth element out of the array, and that's it. I'm just going to run that. I'm going to return the sum. So this one's a little bit more involved. What is it doing? Yeah, Cadence.
Is the return, it would just return the last sum of 1 of j, right? Like,
Yeah.
you keep resetting it back to 0.
Yes, yeah, and let's say that this is the array size here. So how many, so we come in and I equals 1 on the first pass, and this just runs once, right? And it literally just adds the first array element to the sum, so it actually just does one addition. And then it's, I guess actually I do want to spit that out. Let's put that inside this for loop here. Return sum. Because I want this to happen inside this loop here, so this is also indented. And then when I equals 2, this loop is going to run twice. And so it's going to add the first 2 elements and then print that sum out. So like for example, if my array looked like this, it was 3, 5, -1, 2. Then the first time through, this thing is going to print the sum just 3, so it returns 3. The next time through, it adds 3 plus 5, so 8. Then it adds the next 3, 7. And then it adds all 4 of them when I is equal to the array size, and it's just going to return a 9. But let's think about what it's doing here. The first time, it's adding just 1 number. Here it's adding 2 numbers. Here it's adding 3, and here it's adding 4. In total, the numbers. So how many numbers has it added by the end of this whole loop? This sum right here, right? So at the end, the total adds is going to be, what does that add up to, 10? Even though the array size is just 4. So how does this thing operate as that array size increases? What kind of response do we expect in terms of the processing speed? And here I'm going to show you what this one's going to look like. And then I'll prove it to you a little later. So this proc, or sorry, I already got my proc. So here's n, this is my array size. And then here we have some processing speed. This one's going to look something like this. As the array size increases, I'm not going to make up fake little. So I'm going to see a really different behavior than I did on the previous ones. Does that look like a line? No, that doesn't look like a line at all. In fact, this is more of a parabola here. So, but it gives me a sense of how fast the time required is growing as the data set increases. So this one, there's really no worries, right? Maybe get a faster machine if you wanted to go faster. On this one, concern, it makes sense that things get bigger as the required work gets bigger. But compare that to this one. How does this one, the new one, compare to the old one? And if you put them together, you'd see that this one is growing way faster than that line one. A lot faster. And so today, all we're going to talk about is how do we quantify this? What is it, and what does the notation? How do we maybe understand that notation and do something useful with it? So, I've got nice different notes for today. We're going to use big O notation to describe these various behaviors. And there's actually three notations. There's big O, there's big theta, and big, forgetting the Greek letter. What's the other Greek letter? Oh, omega, yeah. Okay, so we're going to use big O notation. And I think sometimes people write it like this, just so it doesn't look like a zero, but big O notation is used to communicate worst case growth. And it's really important that we add that worst case in there. Worst case growth of processing speed and maybe resources, possibly resources. This could be memory requirements as well. Processing speed and resources versus data set size or number of iterations. So let's talk about what this is. Yep. Worst case scenario. Well, I'm just going to put the definition up. For some reason, I jumped right into it here, but let's just get the damn definition up so we have something to anchor ourselves with. So the definition, I say a function f. So a function f, and that's an f of x. I'll just put that in there for the sake of it. Is big O of g of x. So we've got a couple functions flying around. This is why we spend a little time warming up on them. So this is what I would say. This is the phrase. If there exists, back to the beginning of the class, these constants, C and K, such that, ST such that, f of x is less than or equal to c g of x. And I'm putting these absolute values on. A lot of the times they're not needed because these are always positive quantities, but this is the way you see the definition a lot. This happens when x is greater than k. So let's take that down and just look at it for a second because it's kind of heavy. There's a lot going on in that definition. The good news is you don't need to do anything as intense as that looks to understand what needs to happen here. All right, so for example, oh, by the way, these C and Ks, these are called the witnesses. These are called the witnesses for the big O estimate. So what does this mean? Let me show you with a picture. I think a picture is honestly the best way to understand this. With a nice dark pen. Beauty. All right. So what this is saying is that I've got this function f of x. And maybe it looks something like this. So here's f of x. Now this f of x could be total number of operations required. It could be memory required. Those are the two main things you'll probably see it as. Total number of ops or total memory required. this is the thing that I'm estimating. So function f of x is big O of g of x if this is happening. So what this means is that at some point, let's get rid of this. This might actually even help. At some point, g of x is above, some multiple of g of x is above f of x after some cutoff. So let me show you what I mean by that. Let me get a different pen. I think this is better with multicolors. Here, come on, oh, Jesus. Come on, I guess I have to invest in it. Okay, no? More pens, yes, good. So let's say I have this function g of x and it goes like this. So this red function is g of x. Notice that g of x isn't always above f of x, but eventually it goes above f of x and stays there forever. So, and let's say that this is actually a multiple of it. So this is like some multiple of it. Let's say there's like 10 of those. I multiplied the function g of x by 10. This cutoff point here is the k. So let's see, let's call that a number 2. Let's say that's 7,000. So what I'm saying right now is that f of x is less than or equal to 10 times g of x when x is bigger than 7,000. What this means is that f is big O of g of x. So this is f is big O of g of x. Now a couple points to note. This multiple is not in here. It's the base function. I don't care what the multiple is. But it's actually okay to put it in there. This is also completely legitimate. It's just not done commonly. Because I could use the multiple 1 instead of 10 if I already pre-multiplied by 10. So we've got this. And my witnesses are 10 and 7,000. So it's better to see this with some solid functions. Let's take a look at a few actual examples. All right, so let me show you how to do a big O estimate right now. Let's say, example, that's a good pen. F of x is 3x squared plus 2x plus 1. I want to find an upper bound for this that's above this function eventually. So, goal, find some g of x so that f of x is less than or equal to, and we can just put g of x here, and I'll explain what I mean. After for some cutoff, after blah 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 blah. Sorry. So find some g of x and k of x so that, or just k, so that f of x is less than or equal to g of x when x is bigger than k. So what this just means is eventually and forever. Forever after. So this is my function at hand. What you usually do is start with the cutoff point. So we're going to actually make an assumption. So let's start with the cutoff that we want to use. X has to be bigger than 1. So this is my assumption. X is bigger than 1 to start with. Now I've got to do some manipulations to find an upper bound on this thing. I've got 3x squared plus 2x plus 1. I know that x is bigger than 1. I've got to find something over here that's always going to be bigger. So right off the bat, I'm going to take x bigger than 1, and I'm going to multiply both sides by x. So here, to get from there to there, I'm going to multiply by x. And now I know that x squared is bigger than x when x is bigger than 1. That it's not true otherwise. If you were to look at y equals x, so here's y equals x, and here's y equals x squared, you can see that x squared doesn't actually win until right after
x is bigger than 1. And that's all this is saying, and I'm just doing it algebraically. So now I've got this, which is incredibly helpful. And how about this? We have that 1 at the end. If I square both sides of this thing, x squared is bigger than 1 squared. So in other words, x squared is bigger than 1. Okay, so now why am I doing this? Because here I've got this x squared, and I'm going to try to get everything else in terms of x squared so I can have just a nice simple function and a multiple. So, first off, 3x squared, I'm going to just copy that over. I'm not even doing that. This is true because I'm allowed to have equality. 2x is less than 2x squared. Do you see how I'm getting that? Because this, multiply both sides of this by 2. If x squared is bigger than x, 2x squared is bigger than 2x. So let's put that little note here. 2x squared is bigger than 2x. And now I also know that x squared itself is bigger than 1. So plus 1, so this guy right here is because x squared is bigger than 1. So now I've got a bound, I meant x squared there. I've got a bound in terms of x squared for each of these 3 terms. I can add them all up, and I've got 6x squared. So what that means is that this function, it's a parabola, right? If you know something about just graphs and things like that, that function, when I graph it, is underneath the function 6x squared as soon as x is bigger than 1. So this is the multiple I don't need to write. I'm going to, so this doesn't need to be written. It's part of the witness package to be included. What we're going to say is that 3x squared plus 2x plus 1 is big O of x squared. Because I bounded it by a multiple of x squared. So because 3x squared plus 2x plus 1 is greater than or equal to 6x squared when x is bigger than 1. So here's my witnesses. Witnesses are 6 and 1. So it's tricky actually. To come up with these estimates is a hella tricky thing. You need to know some tricks, and this trick gets used a lot. Let's do another one. What if I had started with a different cutoff? So let me show you what happens then. Let's say now we're assuming x is bigger than 2. That's going to change everything. So what if we assume x is bigger than 2? Okay, so let's look back at what we had here. It's kind of the same rhythm. Multiply both sides by x. So x greater than 2 implies x squared is greater than 2x. There I'm just multiplying each side by x. And how about this? Is this true? Because I'm looking for a bound on that constant part. This is going to help me get a bound in terms of x squared on the 2x part. What about this? Is this true? What is our x squared actually bigger than? So I know that x is greater than 2. What is x squared actually bigger than? X squared, yeah, so square each side. So x squared is bigger than 4, actually. So check this out. So we got this because our x squared is actually greater than 4. So it's certainly bigger than 1. So now I put these all together. I'm going to get a slightly different formula here. So 3x squared plus 2x plus 1 is less than or equal to, I'm going to copy the 3x squared again. The 2x is bounded by x squared this time. And the 1 is bounded again by x squared. So now check this out. I got 5x squared. And so this happens when x is bigger than 2. But it still means the same dang thing. I still write f is big O of x squared. Because eventually, it's underneath a multiple of x squared. That's the key thing. That's what you need to remember. Eventually, this is bounded by a multiple of x squared. And that's a really nice way to say it. Let's do one more. Because you can really do this badly, too. It's always easy to estimate poorly. We have no problem with our human brain of estimating things terribly. That's why they have contests to estimate the number of gumballs in a jar and things like that, or jelly beans in a jar. So let's just put a little note here. Can easily overestimate. So, for example, suppose, I'm going to go to a little simpler thing. F of x is 3x squared. Let's say I'm starting with, I got to pick my cutoff, so I say, okay, let's start at x greater than 3. So assume x is greater than 3. Okay. So wait, let's see where I was going to go with that. So multiply both sides by x squared. Multiply each side by x squared to get x cubed is greater than 3x squared. There we go. So now all of a sudden, I've got this function. So f of x is less than or equal to x cubed when x is bigger than 3. And that means f is big O of x cubed. Isn't that a terrible estimate? Yeah, Cadence.
So did you try to make like that 3 on the right side of the inequality into 3x squared?
Yes. Yes, sir. Yeah. Oh, you mean to get from here to here? Yeah, I was taking my cutoff and trying to manipulate it into relating to the original formula. Yes, okay. Absolutely. This is a stupid estimate. This is pretty bad because look, there's actually something simpler. So this is a really bad overestimate. It's okay. We know something about f because of this. I know that it's under a multiple of a cubic function, but we could also do this. F of x is just 3x squared, and that is literally less than or equal to 3x squared when, hell, x is pretty much anything. When x is bigger than 0. It's equal to itself. So f of x is big O of x squared. And that's a much better estimate. When you look at a squared function, so here's squared, here's cubed, you can see that this thing blows up so much faster than this one, and what you want is the best estimate possible. So shoot for, you'll probably never be making these estimates on your own. You'll be given them generally. Shoot for the tightest estimate. But know that it's also okay. Like, that's a legit statement. There's nothing wrong about that. It's just not as helpful. All right, where are we going next? That's 2, 3, okay. Here, I've got my pages. This is a new style for me. And all these damn pages. Let's take a look at something that's a false statement. All right, so, or I guess it's a true statement. Another example. It's kind of an anti-example. Anti-example. I wouldn't say counter-example, really. So f of n is n squared. Let's start getting in terms of the variables we'll probably actually be using. This f, well, actually, what big O is that? Give me a big O estimate for this f. F is big O of what? get too crazy with it. What's a big O estimate for that? Kyle?
N squared?
Perfect. It's just, yeah, n squared. It's just, yeah, beautiful. So this function is n squared. And if you sketched it out, it looks like a parabola. So here's n squared. Here's n, there's your output, n squared, yield parabola. F is not O of n. And I'm going to have to actually pull up a graphing utility to prove this to you. So let me get that. Oh, this damn thing locked up on me already. Come on, don't lock up. Yay. Yay. Let's see here. Let's get a little power. Just fuck that up really bad. Now it's going to take a while. Okay. So I'm going to go to Desmos. Does that look like it's coming on at all, that projector?
Sounds like it.
Oh, awesome. A little bit. Sounds good. Let's go there. Oh yeah, beautiful, beautiful. So let's take a look at n squared, and then let's actually learn some really important comparisons using this app. So first thing I'm going to plot out is just n squared. I wonder if I can just type n squared here. Probably not. No, I've got to type y equals. So y equals n squared. There we go, yield parabola. Let's actually just assume n is positive. So I'm just going to look at that half. Let's actually pull it down a little bit. So to say f is not order little, just n, is to say this. I can never find a multiple of n that is bigger than n squared forever after some point. So there is no n and k pair, or excuse me, c and k pair such that n squared is less than or equal to c times n when n is bigger than k. Let's prove that. So let's take, we can do a parametric thing. So let's look at y equals a multiple of n, so cn. And see, it gives me a little slider. Yeah, I want to add a slider, absolutely. And I'm going to change this slider to have a different range. So let's start at 0 all the way up to, why not say 100? What the hell? And we're going to step by ones. Alrighty, so the blue line is the thing that I'm claiming is not the order of n squared. And you can see that even though right down here the line is above, right? So right there it's like, okay, it's above, but eventually it falls underneath. And you think to yourself, well, maybe I just need a bigger multiple. So you just add, you double it. Okay, oh, that looks pretty good, right? That looks really good. And then I back out and realize, oh shit, it fell under. So that's not working, because it has to be above forever. Okay, well, certainly 4 would work. Oh, how about just 10, right? 10, there we go, 10. Oh man, there's no way that parabola rises above that line. Oh yeah, look at that, looking good, oh, it's looking bad, looking grim, yeah. So eventually that's gonna lose out, no matter what I make this multiple, no matter how steep that thing looks. All I have to do is actually zoom out far enough, and this actually might, oh, there you go, you can see it, right? You see that the blue line is eventually under the parabola. So this can never work. I can never find a multiple of n that will beat this n squared at some point and forever. What about a different power of n? Let's try something else. What about if I had, let's get this guy back down. What about n cubed? Like we were saying before, so here's n cubed. Oh boy, oh, the scale is all fucked up. How do we, let's home it, there we go, okay. So now, blue is the O, the big O thing that I'm talking about. And here you can see that n squared is totally order big O of n cubed, right? That's not a problem. No matter how far out you back, you can see they're getting further and further apart. That's looking good. So there's a hierarchy of big O functions, and let's take a look at what those might look like. I'm going to get rid of this slider, and let's compare some things. So let's first start off with maybe one of the lowest orders, just a constant. There we go. I'm just constant. My runtime never changes depending on my data size. So it depends on the processor speed, but nothing else. And then what about maybe a square root of n? How does that look? Aha, so that's a very different growth than we've seen before. It's almost kind of horizontal, but eventually it's above that order 1. Let's do just plain old n, y equals n. So you can see that that pulls far away from that square root of n, and definitely is an upper bound on square root of n for most values of n. What about this one? Log of n. Where's that going to fit? Do we understand logarithms? No. Okay. Case is telling me no. Okay, we'll talk about that a little bit because that's actually important to understand. So let's say y equals log n. Now check that out. That's actually under the square root of n. Notice how that black line there is above the constant, but it's below the square root. In fact, it's actually below any root of n at all. So like, what if I had n to the 1/10 power? So 0.1. So now that's the blue graph, and you can see that the black graph is actually above it. So it's above almost any power of n, any fractional power of n that you can think of. So let's put this back to n squared. Here's n squared. Let's get a y equals n cubed in here. And let's pull back out. So we're seeing a bunch of different ones here. Log n. I think I need to clean this up. Let's get that out of there. Let's get that out of there. Get that. How about this? Y equals n log n. So that's n times the logarithm of n. And I will explain what log means in just a minute. So check it out. That is the blue one, right? Oh my God, what different colors are they? Let's change the color. Oh, it's that one. There we go. So notice that that n log n is above n. So it's above the purple graph, but it's also below the n squared. So it kind of sits between a line and a parabola. And then here's one that's just going to blow everything away. If I just take any number and raise it to the n, this is called an exponential function. That's the green one, and it is beating x squared like furiously. Let's see if it beats a different power of n. What about n to the 20th? Well, let's see if this can work here. We might not be able to see that. Holy shit, let's see, turn it off. Okay, so n to the 20th is that blue line that looks almost vertical right there. And what I'm claiming is that 2 to the n eventually is above it. And we might have to go, this might be not worth our time. I think I picked too big a damn power here. Let's just try into the 4th so we're not here for the rest of our lives. Let's see, so, yep, so will that exceed n to the 4th eventually? Do they look like they're getting closer? Not really, do they? Is there a better way to do this? Probably. Oh, there, yeah. Yeah, let's go. So that 2 to the n, oh, now I can really get up there. Let's zoom in. Did it beat him? I don't even see it on the right side anymore, do you? Okay, well, that's become a clusterfuck. All right, so let's end that because I'm just having my jollies here. Let me summarize on the board what I'm trying to actually tell you. Here's a little cheat sheet for big O guide, for big O bounds. Good old cheat sheet here. Cheat sheet. Okay, so cheat sheet. these are big O estimates in order of size. So these are stacked accordingly. So this is the lowest one. First off, we have big O of a constant. So this is constant response. This was this one here. No change in processing time. Then we have big O of log of n, and I will explain that in just a second, Cadence, what that means. Then above that is big O of n, so any multiple of n. Then above that, we've got n log n. Then above that, we've got big O of n squared. It's a very common one. And then higher powers of n, so like n cubed, n to the fourth, and so forth. So here, let's just put big O of n to higher power. And then above that are the exponentials. So I've got 2 to the n, or any number to the n. So order 3 to the n. So notice here the n has become the exponent. Here it's the base, here it's the exponent. And then above all of that is big O of n to the n. And that's really crazy. Let's just think about what n to the n looks like. You will occasionally see it in really intense algorithms. But n to the n looks like this. If here's n, so 1, that's 1 to the 1, that's 1. 2, this is called tetration, by the way. That's 4. When n is 3, that's 3 cubed, that's 27. When n is 4, that's 4 to the 4th, that's 256. When n is 5, that's 5 to the 5th. Anybody got a calculator on them? I don't know what that is.
Give me a second.
Thank you.
Uh, 3,125.
3,425?
125.
Is that what'd you say?
3,125.
125, thank you. And then one more, please, Yvonne. Can we just do 6 to the 6th? Because I want you to see just how fast these things are growing with each step.
46,656.
Okay, that's really intense. When you compare that to something like n squared, so check this out, that's just 1, 4, 9, 16, 25, 36. You can see that it's just blowing this one out of the water. Let's actually do, now let's not do that. That's a good little cheat sheet. There's one more that I want to insert in here before I talk about what log means, and it's big O of n factorial. That's a really useful one as well. Should I explain what factorials are? Should I talk about that? Yeah. Let's start there and then we'll go back to log. So factorial, and you'll see this notation pretty often in your computer life, is just a multiplication. It's just a shorthand for a repeated multiplication. So if this is n, then here's n factorial. So 1 is just 1, 2 is 1 times 2, 3 is 1 times 2 times 3, 4 is 1, 2, 3, 4. So it's just the product of all the whole numbers up to that number. So this is 24, this is 6, and this is 2. And then the next one, 5 is 120, 6 is 720. It gets big really fast, but nowhere, you can look here, nowhere near as fast as this crazy sucker right here. But it's definitely also faster than this, eventually. Where am I going with this? What am I doing? I got my stupid little chart that I put there. I don't think I'm going to pull that out anymore. And let's just look at a solid example here and do a big O estimate of like an algorithm. You're not going to have to do anything too intense with big O in our classes. Probably not in your CS classes unless you go get a master's or something like that. Usually these things are kind of all figured out in advance. But what if I had f of n, so here's an example, is the sum of the first n integers. So 1 plus 2 plus 3 plus n. Let's find a big O estimate for this. For how this thing is growing. So this is analogous to that last piece of code that I showed you, where each time we went through, we were adding another integer. So the first time you're only adding one thing, then next time 2 things, then 3, then 4. This is the number of operations that that piece of code would go through. So let's try to find a bound. Can we think of one number that all these numbers are less than or equal to? I don't want to use 3, because this might go up to 5. What number are all these numbers less than or equal to? N. Beautiful, right? If this is n, the one before it's less than that, the one before it's less than that. So notice that each one of these numbers is less than n. That's since each number in the sum is less than or equal to n. What does that simplify to? How many n's are there? N of them. So this is n n's, so it's n squared. So this function f, and this is going to be true no matter what. This is when n is bigger than or equal to 1. So f is big O of n squared. And here we have when n is bigger than or equal to 1, f of x is less than or equal to 1 times n squared. So I would give those little details on the side if someone were interested in it. Let's go back to those original algorithms that we had and get their big O estimates. So that was this corresponds to that last algorithm that I had. So in the algorithm where I had the nested loops, this is the complexity, or this is a big O complexity estimate. And that just means time, like how long is it going to take for the nested loop algorithm. Let me explain again why that was, because we had this for loop for I equaled 1 to n, and then in there we had for j equaled 1 to I. And then we were doing the sum equals sum plus the array element, the jth array element. So the first time through, when I equals 1, you've got just a single thing here. So you just have one thing added together. So the sum of one thing. When I equals 2, next time through, I've got the sum of 2 things, right? Because I will equal 2. Sum of 3 things. And each one of these is an operation. So like, how many total sums are there in this whole thing? There's 1 plus 2 plus 3 plus all the way to the last one. When I equals n, it's the sum of n things. So the total sums required are 1 plus 2 plus 3 plus on up to n. All right, so that was our fanciest algorithm. That was big O of n squared. What about this one? We had procedure add array, sum equals 0, for I in the array, add the element to the current sum. What's the order of this? What's the big O estimate on this? Let's just take a minute and see if we can come up with that. How many sums happen in this thing? Let's say our array size is n elements. How will this grow as let's see. So when n equals 1, how many things are we adding? We're just adding one thing. There's one add. When n equals 2, there's 2 adds. There's exactly the number of adds as the size of the data set. So this thing here, this function, the complexity estimate is just big O of n. It just increases. As n increases by 1, the number of operations goes up by 1. It's kind of just a one-to-one thing there. So let me actually go explain logs so that when you see that, and you will, that makes some sense. What is a logarithm? Let's talk about just that word log that you'll see all the time. So the basics of log. So a logarithm is just an exponent. It's actually a shorthand for an exponent. Let me show you the fundamental thing that links this all together. So to understand a logarithm, logarithms, you need this basic identity. So if I say something equals a base b to a power, and these are both numbers, but I like to put them kind of like this, means the same. These both mean each other. So I can actually just put a double-headed arrow. This is an if and only if. They each imply each other. If and only if the logarithm base b of this thing is equal to this exponent. Let me just take a minute, let you write that down, because I'm going to show you some examples. This is the key thing here. And I'm going to explain, you'll see the word log just floating around. Why is there no base on that log? Well, there's a good reason, especially in this particular instance that we have here. So, for example, if I said, what is the logarithm base 2 of 8? You're going to be doing a lot of base 2 logs as a computer science person, right? Have you seen base 2 logs already? Because you have some binary quantity, right? And everything's base 2 in your computer. So this is equal to 3. It's basically what exponent do I have to raise this base 2 to get this number? So you can think of it like this. What exponent is needed on 2 to get 8? This is asking me a question. What power do I have to raise this number 2 to get this one? So what is this? What is log base 10? That's a real classic one of 1,000. What's log base 10 of 1,000? What power do you have to raise 10 to get 1,000?
3.
3, beautiful. Same answer, right? So it's the same power. What about this? Log base 10 of 1/100th. It's a little trickier. What power do you have to raise 10 to get 1/100th?
-2.
-2, solid. So this is equal to -2. So a log can be negative if you've got a fractional quantity in there. A lot of times you'll see, anybody, I know one person who knows this at a minimum. If you see this, Danielle, what's that one? Sorry, I put you on the spot. Like I never had to answer. What do we do? How do you say it? Like, what would you just read it as? ln or natural log, right? So this is natural log. If you ever see this, this is logarithm base e. It's just shorthand. E is a weird number, beautiful number that goes on and on forever. It's like pi, but for calculus. So I'll put an X in here. That's just log base e. So what the hell does this mean? When there's no base. Why no base? because in these big O estimates, multiples of things don't matter. And what this is falling back on is a conversion formula. Here's how you can convert from one base to another. To convert logs from one base to another, use this formula. Log base b of x is equal to log base, bless you, c of x over log base c of b. There we go. Okay, so let me explain this and rewrite it a little bit more. That's just 1 over log base c of b. This is a constant. This is just a number. And then I've got log base c of x. So this tells you how to convert between log base c and log base b. And what I'm really trying to get at is to convert from one log base to another. We just need a multiplier. We just multiply by a number. Just take a multiple. So that's why when we're talking about big O notation, so when you see this, you see something like this. I've got a function and is big O of log base n. I don't need to know the base, because what does this mean? Let's translate it. This means that f of x, or f of n, is less than or equal to some multiple of log base n when n is bigger than or equal to some cutoff point, or just bigger than some cutoff point. It doesn't matter what base I have here, because this multiple can absorb all those possibilities. So let's say I wanted log base 10 here. No problem. I can easily convert that to log base 2. So this is equal to c, so check it out, log base 10 of n, let's put this stuff here, is equal to log base 2 of n over log base 2 of 10. So this is equal to c times log base 2 of n over log base 2 of 10. And this is just part of the multiple. This comes into and gets absorbed by the multiple in front. So what you could say, once you know this, i.e., if I say f is big O of log base 10 of n, that's the same thing as saying it's also big O of log base 2 of n, or any log that you want, log base whatever of n. All these statements are the same, they're independent of the base. The key thing is, what does a logarithm look like? A logarithm looks like this. And a logarithm, if you ever take calculus, you'll find out these become almost horizontal as they grow out to the right. So all logs look like this. They get flat. Not constant, but flat-ish. Let's say flat-ish. Not constant. Okay. Gosh, folks. I don't know if I have anything else to tell you about this stuff. I certainly took up enough time. Is there anything you want to talk about on that Connect assignment? There's one person who's done. There's like 2 people who have started. Do you want me to? Do I need to extend it so I can answer questions on Wednesday? Would that be great?
That's the only homework assigned right now.
It's it, yeah, but there's one more thing that's going to be open, and it's a prep for Wednesday. So on Wednesday, we're moving away from this. We're going to start talking about mathematical induction. And it's our last proof technique. So you're probably gonna wanna be here for that, and everybody's usually here all the time anyway. But this can get tricky, but I'm gonna show you step by step how to set up an induction, and we will be doing some simple ones. Joey, sir.
Yeah, so I'm looking at the connector right now.
Thank
There's
you.
one due on the 19th and there's one due on the 20th.
Oh,
So
what
that
is
should
today?
be Wednesday and Thursday.
That's what we want.
Is that cool?
Beauty.
Okay.
I think we're good to go. So, let's just call it a day. If you have any questions, I'll hang out and talk. Let's meet back again on Wednesday, my friends. We have 5 full weeks till Thanksgiving. Pretty crazy.
For what?
Thank you. Yeah. Sounds good. Yes, sir.
So with the higher is the O of N to the power of N, is that what's the least efficient or most time consuming?
That's absolutely, yes.
So it just goes down.
Yes, yeah, this is the worst performance.
Okay.
Yeah. So, and this is like great, because then, we're ready for anything, and
Yeah, like that's.
however fast we optimize
I
the
gotta
code,
just-
it won't change.
I'm trying to just
depending on the
jump
days.
for it now.
Okay, gotcha.
Does that make sense?
Yeah, I just wanted to double check that real fast.
Yeah,
I don't
that's good.
understand,
Yeah,
like-
good stuff.
I did you?
Thank you, sir.
I'm just trying to jump for it now. I'm just saying like.
It would be great to have you in class.
I'm not that fucking
Yeah.
stupid.
I'm not looking forward to it.
Yeah.
Smarter than, like.
You're not? Have you had, what's your background like?
I mean, I've done pre-calc like twice, one at high school, one at a college level, I just have been avoiding it.
Really? Okay. So make sure to take the Alex pretest. So I would actually start on that now. If you're thinking about it, gosh, I don't teach Calc 1 for a while. I was like, do I teach it next fall?
Yeah. I think with my timeline, I have to take it next semester,
Okay, yeah.
which is not bad. I should do it.
No, I think if you can take it with, well, let's take a look, oh, let me shut this down. Let's take a look at the, who's teaching it next semester, and I can make some recommendations.